Okay, hi. This is the review of your OS task. Okay. It's a job is being handled from start to finish by four sets of concurrent processes called keyings, verifiers, computers, storers. The keyings input data into a buffer called buffer1 large enough to take 750 equal size items. These are four concurrent processes. The keyings are accessing a buffer1 large enough to take 750 equal size items. The verifiers accept data from buffer 1, verify them, and deposit their outputs in buffer 2, large enough to take 670 equal sized data items. The computers take verified data items from buffer 2, perform calculation on them, and deposit their results in buffer 3, which is large enough to hold 750 equal sized items. Finally, the storers take computed results items from buffer 3 and store them in an external disk space provided for the purpose. 9 semaphores are involved as listed below. 1, 2, 3, 4, 5, 5, 6, 7, 8, 9. These are the 9 semaphores. Item 1 is an acronym. Item availability 1, which ensures that a verifier can enter and extract data from buffer 1 only when the data item is available. Item 2, which behaves similarly as item 1 for a computer and buffer 2. So this is for buffer 1 verifier and keying for buffer 1. Okay, this is similarly for computer buffer 2, which is behave similar. Okay, blah blah blah. Write down in order the initial values of the 9 semaphores. Okay, if 3750 items have been deposited in buffer 1, find an expression for the possible number of data items V that must have been verified. If this is okay, if these items have been available in disk space, find an expression for the possible number of result items that must have been deposited in buffer 3. Write for concurrent algorithmic program for the four sets of processes. Okay, what primarily is happening here is you have four processes running simultaneously, concurrently, checking a buffer. The verifier is checking buffer 1, keying is checking buffer 1. The buffer 1 has to be implemented in a mutually exclusive fashion where it only accepts only one access at a time. It's either the key in is accessing the buffer 1 and entering a data item, or the verifier is accessing buffer 1 and extracting a data item, for verification. They can't access the same time. So now the bottleneck or the limiting factor is buffer 1 for between key in operation and verifier operation. This is important. Okay, good. So that means the key needs to check the buffer. Are you free before I drop any data, store any data in you? The verifier needs to check, are you free before I extract any data from you? Now, the buffer needs some sort of technique to broadcast its current state, busy or free. And the means which is doing this is semaphores. The semaphores are non-negative integer variables which are used like flags. Semaphores actually mean flags, the name, the English word semaphore, how it's even implemented, used in our normal life is just like flags. Let's check the definition of semaphores. Semaphores definition. A system of sending messages by holding the arms or two flags or poles in certain positions according to an alphabetic code. So you can see these are non-integer variables sending messages by the values they are holding. Okay, good. So our first task is to write down in order the initial values of these semaphores. There are two types of semaphores. You have the counting semaphores and you have the binary semaphores. Counting and binary semaphores. So we're going to use a mixture of counting and binary semaphores to answer this question. So different people might have different solutions. I actually looked for a lot of possible answers to these questions online and I couldn't find, but eventually I got something that pointed me in the right direction from the lecturer's own text. Okay. Alright, so the keys in checks the buffer. If there is space in it, if there is nobody accessing it, it drops the keys in data. If the verifier is not extracting data, it can only key in 750. If it keys in and the verifier is checking concurrently, once there is no keying operation going on, the verifier extracts the data stored, keeping the space back to 750. It was initially 749 when it keyed in. As the verifier took the one data out, it increased back to 750. So we are working with 750 plus or minus as long as the verifier is working. Good. Computer, same thing, but for 2 it's working with 670. But for 3, between computer and store, 700. We check for availability of space. We check for mutual exclusivity or free, or if the buffer is free. Okay, we check for, basically that's a space, item present to extract, just like that. We'll see it in the flow chart I used. Okay, so let's go to the solution. Great. Solutions, write down in order. Nice one. The semaphores are a combination of binary and counting semaphores. Binary semaphores are initialized with either zeros or ones. Counting semaphores are initialized with non-negative integers. So since my initial space for 1 ensures the buffer 1 limit of 750 equal size item is not exceeded, once you get to 0 and any other keying operation tries to make it 0, because wait signals on semaphores, you have two procedures, two operations: the signal and the wait. You call the signal, you're incrementing the semaphore by 1. You call the wait, you're reducing it by 1. You're telling the semaphore that, okay, I'm taking a portion of your space, or I'm utilizing this process. So if you cannot accommodate any other process, then it's going to be a binary semaphore so one process at a time. But since this has to do with space, I'm reducing it by 750. Then for the boomer, since it's mutually exclusive, it has to be 1, so that once a keying or verifier accesses the boomer, it turns to 0. If the verifier goes in when the keying is already accessing the boomer, the buffer, it's going to be negative, so it will wait until the keying operation is over. So just like that. The item available, it's initialized to 0 because at the start of the process, at the beginning of the program, there is no keying operation, so there is no item That means the verifier cannot gain entry into the buffer because there is no item. There will be an error. So to prevent this, you initialize it to 0 so that when the verifier checks no item available, there's no point checking the buffer. Okay, and so on for the remaining processes. Likewise for space availability 2 for second buffer, you need to verify and send into buffer 2 for computer to extract and compute. So the same thing happening in space 1, buffer 1 and Itava 1, the same happening in space 2, buffer 2 and Itava 2. Likewise 3. Okay, so that's why we have this. These are the sizes of the buffers. If 3,750 data items have been deposited in buffer 1, find an expression for the possible number of data items v, which must have been verified. Using this equation, 0 is less than or equal to d minus e is less than or equal to n, where these deposited items, 3,750 items, and e is extracted items, which is equals to v for verified items. N is equals to buffer 1 capacity, which is 750 equal size items. Expression for possible verified item will then be 0 less than or equals to v less than or equals to d minus n. Substitute into the equation 2, this, and this. So the verified items is 3,000. This equation was gotten from the lecturer's book. So verified items is 3,000. This is plain and simple from this equation. Number of deposited items on the buffer, number of extracted items from the buffer by the next process that's extracted from the buffer, and capacity of the buffer. Okay. 2. Likewise. So it's just using the same equation. Okay, using equation 1 again and solving for items deposited this time. The question is find expression for the possible number of the result item S that must have been deposited. This results was stored. This was stored from buffer 3, right? This was stored from buffer 3. So what was extracted? What was deposited? This was like what was extracted and stored. So what was deposited was just less than S from equation 1 again, which is this. Okay, this was stored. What was deposited? The buffer capacity plus what was stored, n plus s, d. Okay, so that is it. Item stored, deposited. Okay, right. For concurrent, I go like program for the concurrent. Okay, this is the interesting part. You have different school of thoughts from here, but if the lecturer will eventually say something about this, I don't know. But this is the correct solution so far. Makes a lot of sense. Repeat indefinitely. Algol-like. This is Algol-like, not a particular programming language, but it looks more like Algol 68 family of languages. Very old. Okay. Procedure keyings. Repeat indefinitely begins like reduce buffer 1 by 1. Note the limit is this. You call wait, it's reducing it by 1. Block buffer 1 to ensure only one process accesses it. You're waiting space wait boomer. Okay, reduce buffer 1 by 1. Begin, you extract it, there's space for it. You block the buffer, you deposit an item. This is the critical section. This provides mutual exclusivity for this operation. You deposit an item in the buffer. Okay, you release the buffer 1 to ensure only one process accesses it. Now you're done with the buffer 1, so you release it. Okay, you release the space signal. Okay, signal space available, yes. You deposit your item. data is now available to extract. You signal iterval1, that's item availability 1. Remember, this iterval1 was initialized to 0. Okay, was initialized to 0. You know, one good thing about explaining these assignments to yourself is you tend to see your mistakes, if there are any. Okay, so reduce buffer 1 by 1, notice limit. Okay, reduce the comment, you reduce buffer 1 by 1, block buffer 1 to ensure only one process accesses it. Okay, you deposit your item, you signal, you release the buffer. What are you signal? Release space on buffer 1. Who is supposed to release the space? It's not the verifier, extracts the data. This is, wait, buffer 1. Wait, gonna have to pause this video here and clarify this out, then I'll be right back. Okay.